Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the class again. So today we will be discussing about two small topics. One is Degenerate Cope rearrangement reaction and the other is Oxy-Cope rearrangement reaction. So coming to the Degenerate Cope Degenerate Cope rearrangement first. So we need to see what is degeneracy. So we might have heard this term degeneracy or degenerate levels or something like that so many times, several times. So what does it mean? Means if two energy levels are there and if they are having same amount of energy, same energy, we call those energy levels as degenerate energy levels. So the basic example, the typical example is, so d orbitals after splitting in the octahedron field, so we'll split into two types, two sets. One is T2G set and the other is the EG set. So in the T2G set, you can always see like 3 d orbitals having the same energy are taken as the set, T2G set, and two remaining d orbitals are considered as the EG set. So why they are grouped like this means they have the same energy. So they are degenerate energy levels, right? So similarly, now coming here, the degeneracy is a little bit different when compared to the what we have discussed now in the inorganic chemistry. So degenerate Cope rearrangement means when it is indistinguishable. What is indistinguishable? If the reactant is indistinguishable from the product, so that means which looks alike, the reactant as well as the product are almost equal. So you call it as degenerate Cope rearrangement. So the typical example which refers to this point, the degenerate Cope rearrangement, has been already discussed. So the example is the 1,5 hexadiene. So this is a 1,5 hexadiene, so which undergoes 3,3 rearrangement under thermal conditions. So the arrow mark should be shown like this. 3,3 shift is happening under thermal conditions. So the product is this. So it is difficult to differentiate these two, reactant as well as the product. So therefore it is treated as degenerate Cope rearrangement. It is treated as degenerate Cope rearrangement. Similarly, there is one more such molecule which absolutely shows the degenerate Cope rearrangement, that is 3,4 homotropylidine. So it is a bicyclic molecule where you can see the 7-membered ring, 1, 2, 3, 4, 5, 6, 7. So it is a 7-membered ring. It is potential enough to undergo the Cope rearrangement because it is resembling the 1,5 diene system. So therefore 1, 2, 3, 1, 2, 3. So therefore it is capable of undergoing the Cope rearrangement. But what is happening here in the 3,4 homotropylidine is, you can see a cyclopropane structure here, ring structure. So in its cis form, it undergoes 3,3 rearrangement very rapidly. So it undergoes 3,3 shift very rapidly and then gives the product this one. So this is the product and this is the reactant molecule, so which is shown by 3,4 homotropylidine system. So, the sigma bond which is migrating is this one, 3 to 3. So, this is moving like this and this is moving like this and this is forming a sigma bond here. So, therefore, you are getting the pi bonds here and a new sigma bond over here. But it is quite impossible to distinguish these two products by looking at their structure. So, this is the best example for the degenerate Cope rearrangement. So, where from you can say that the cissoid form of this is absolutely happy to undergo this degenerate Cope rearrangement means if you look into divinyl cyclopropane. So, if you look into divinyl cyclopropane, this is the system which can easily undergo the Cope rearrangement if both the vinyl systems are in cis to each other. So, but actually in order to have this stability, it prefers to be in trans form, right. So, but once it is in the cis form, it happily undergoes the 3,3 sigmatropic rearrangement. So, what was observed in this reaction is the systems which are undergoing such kind of 3,3 sigmatropic shifts previously, what we have seen is they prefer to be in the chair conformation. They prefer to be in the chair conformation, so which is energetically more stable. But in this case, the chair conformation is not suitable for the formation of the cyclic transition state, thereafter the product. Rather, this type of molecules will prefer to undergo the 3,3 sigmatropic rearrangement reaction via the boat-like transition state, So, the reason here is if it has to undergo the reaction via the chair-like transition state, then it is likely to give a 7-membered ring with the double bonds in the trans conformations. So, which is increasing the destability of the molecule. So, that is why they prefer to be undergoing the 3,3 sigmatropic rearrangements via a boat-like cyclic transition state. So, the homotropylidine molecule, 3,4 homotropylidine molecule will exist in two different forms. One is the transoid form and the other is the cissoid form. So, if you look into the transoid form, this is the double bond and this is one more double bond and these are the hydrogens, right. So, this is the sigma bond which is likely to undergo the migration or 3,3 sigmatropic shift 1, 2, 3 and this is 1, 2, 3. So, this molecule is in transoid conformation. So, if you want to look at the cissoid conformation, so then the molecule will look like this. So, the hydrogens are in this way and this is another double bond. So, this is the cissoid conformation. So, among these two, transoid and the cissoid conformation, so cissoid conformation readily undergoes the 3,3 sigmatropic shift compared to the transoid form. So, the best example to justify this is the conversion or the degenerate Cope rearrangement shown by 9-barbaralone. So, 9-barbaralone is a molecule which shows the 3,3 shift under cissoid conformation. Okay. So, let us see the transformation or the 3,3 shift shown by the 9-barbaralone molecule. So, this is the 9-barbarolone molecule where there is a carbonyl function here, and this is the sigma bond which is likely to migrate 1, 2, 3 and 1, 2, 3. So, under thermal conditions it undergoes 3, 3 shift. So, this is in schizoid conformation and therefore, it readily undergoes rearrangement. So, now this sigma bond has migrated to this place and the double bonds have moved here, right. So, what is happening? So, this sigma bond is shifting over here and this pi bond is coming here as a sigma bond between the 3 and 3 and this one is migrating here. So, if you want to see the cyclic transition state, so this sigma bond is slowly vanishing here and then this pi bond is forming a sigma bond, new sigma bond here and this pi bond is moving over this place. So, this is the cyclic transition state which is typically showing the boat like transition state. So, this is the boat like transition state, especially happens in the schizoid conformation. Okay. So, if you are given a set of some molecules like this, which is divinyl cyclopropane, this one, so can you quickly identify which is the molecule capable of exhibiting the or undergoing the 3,3 sigmatropic rearrangement, which also can be seen as a degenerate Cope rearrangement? Which one? So, this example we have seen earlier. So, this instead of the chair like transition state, it undergoes the reaction via the boat like transition state and the product will be like this. So, if it is moving here, so you will be getting a 7-membered structure which is similar to this one. This again can undergo the 3,3 sigmatropic rearrangement and gives a product similar to this one. So, this is the only molecule where this particular sigma bond can give you the degenerate Cope rearrangement. Okay. So, this again cannot give the degenerate Cope rearrangement, it gives a 8-membered ring structure. Okay. So, that is the thing with the degenerate Cope rearrangement. Now, let us quickly move to the Oxy-Cope rearrangement. So, what we need to see now is Oxy-Cope rearrangement. So, what is the basic difference between a normal Cope rearrangement and an Oxy-Cope rearrangement means? So, an Oxy-Cope rearrangement can be seen in the case of a 1,5 diene. So, this is the typical 1,5 diene which under thermal conditions can give you the Cope rearrangement product, that is the 3,3 sigmatropic rearrangement will occur here. If the C3 carbon atom of a typical 1,5 diene is given an oxygen functionality, for example OH group. So, this is the C3, C1, C2, C3, C4, C5, C6. So, this is 1,5-hexadiene skeleton. So, on which if the C3 carbon atom is provided with an oxygen functionality like OH group, then the normal Cope rearrangement what is happening here, same, the exact same thing will be seen. But what is the difference is the presence of an oxygen functionality at the C3 carbon atom will pronounce the reactivity of the Cope rearrangement, will enhance the reactivity of the Cope rearrangement, while the product remains this way. So, this is the product. So, what is the reason behind this? Means before going to the reasons why the presence of an oxygen functionality is rapidly increasing the rate of reaction towards the right hand side, we have to compare the normal Cope rearrangement with the Oxy-Cope rearrangement. So, a normal Cope rearrangement will have a normal reactivity. So, in the beginning itself we have also discussed like the nature of the substituents on the C3 or C4 can rule the reactivity of the Cope rearrangement. So, without any substituent on the C3 or C4, the Cope rearrangement is a normal one. So, in the case of Oxy-Cope rearrangement, the reactivity increases. Reactivity increases because of the presence of this oxygen functionality. Okay. So, the temperature required to perform a Cope rearrangement is generally around 300 degrees centigrade. So, whereas due to the presence of an oxygen functionality, the temperature required to drive the Cope rearrangement here is in between 150 to 180 degrees centigrade only. You can see the change. So, how the temperature required to drive this normal Cope rearrangement is so high, and with the simple substitution or the introduction of a oxygen functionality on the C3 has decreased the required temperature to half or almost half of the thing. One thing also we have seen, that is these are reversible reactions. So, most of the pericyclic reactions are, almost 90% of the pericyclic reactions are reversible in nature, right? Whereas the Oxy-Cope is irreversible. So, the reason for increase in the reactivity or requirement of lower temperatures to perform the reaction, or the reaction itself becoming irreversible, is if you look into this molecule, it is capable of undergoing tautomerization. It is capable of undergoing tautomerization. Means what? So, it can convert into a carbonyl compound. It can convert into a carbonyl compound. So, the ability of the product, which is formed after 3,3 sigmatropic rearrangement, is having the ability to tautomerize. So, the ability of the product to show tautomerization after 3,3 sigmatropic rearrangement is the driving force for its irreversibility, for decreasing the required temperature or high reactivity compared to the normal Cope rearrangement. Normal Cope rearrangement, right? So, why it is happening so means, so the product which is seen after tautomerization is highly thermodynamically stabilized one. Thermodynamically stabilized one. So, that means if this is the reaction where the energy of the reactant is exactly equal to the energy of the product, so it is always reversible. So, if the same reaction is happening this way, where the energy of the product is much lower compared to the energy of the reactant molecule, we call these kind of products as thermodynamically stable products. These are thermodynamically stable. So the formation of the compound with a carbonyl function makes them thermodynamically stable. So this is the reason why the Oxy-Cope rearrangements are irreversible in nature. So what if before undergoing the 3,3 rearrangement, if I add any base, if I add this one, so what happens here is it becomes this one. So one question you may ask me here is, we have already discussed like no pericyclic reaction will involve in the generation of an ionic species, right? So but if the reaction itself, if the pericyclic reaction itself starts with an ionic species, then the ion or the charge will be carry forwarded until the product formation. Okay, so it will not neither create a new ion, or it will not use up the ion existing. So it will be simply carry forwarded from the reactant to the product. So if you have converted this into an anionic species, right? So by deprotonating it in the first step itself before undergoing the 3,3 sigmatropic rearrangement, then also it is quite capable of undergoing the 3,3 sigmatropic shift and give the product like this, right? So or which can undergo minus double bond O, this one. This will be happening inside the things. So once if we protonate it again, so you will be able to see this product only. So the difference between this and this is, it is happening under the normal conditions, whereas before undergoing the 3,3 shift, you are deprotonating the 3-hydroxy 1,5-diene, so which is able to show the Oxy-Cope rearrangement, and as a result of which the reaction becomes super reactive. So compared to the normal Oxy-Cope rearrangement, it becomes approximately 10 to the power of 15 times faster in reactivity, and in the previous comparison to the normal Cope rearrangement and to the Oxy-Cope rearrangement, we have seen about 40 to 50% of decrease in the temperature requirement. But in the case of anionic Cope rearrangement, so this is called as anionic Cope rearrangement. So in the case of anionic Cope rearrangement, the reaction can happen even in the minus degrees. So this particular reaction can happen at around minus 78 degrees centigrade. You see the change now. So just because of deprotonating the proton molecule, so the reactivity has pronounced like anything, which is almost approximately 10 to the power of 15 times faster than the Oxy-Cope rearrangement reaction. So the reason here is, so because of the presence of an anion here, so the cyclic transition state which is going to be formed during the conversion of this product to the reactant to the product, so becomes highly stable. So the transition state is becoming highly stabilized. So as the transition state is acquiring extra stability, the reaction always runs towards the right hand side. So in addition to that, the lone pairs donated by the oxygen, which is adjacent to the carbon-carbon sigma antibonds to the antibonds, will weaken the bonds to be broken. So our idea is to break the sigma bond from one place and then shift it to the other end, 3,3 position. So this will be supported by the capability of the oxygen to donate the lone pair of electrons to the say carbon-carbon sigma bond antibonding orbitals, so which weakens the or which minimizes the energy required to break the sigma bond. Okay, so that is the reason. So if you can quickly try some of the examples of Oxy-Cope rearrangement, so we'll be done with this. task. See this example. So this is a typical example of Oxy-Cope rearrangement reaction where the C3 carbon atom is having the oxygen functionality. So this can always undergo 3,3 sigmatropic rearrangement, and the product will be this one, or after tautomerization this one, right. So after undergoing tautomerization, you will end up with the carbonyl compound. So before tautomerization, the actual product of the 3,3 sigmatropic Oxy-Cope rearrangement reaction is this one. So which is always capable of undergoing or showing the ketoenol tautomerization. So in the chair form, if you see this, so this is the molecule. So what is happening here? So this 1, 2, 3 and 1, 2, 3. So this is the sigma bond which is migrating. So in the cyclic transition state, what you can see is, so the sigma bond over here is slowly breaking, and then a sigma bond here is slowly forming. So this becomes the cyclic transition state, and after that the product is this sigma bond has gone, this sigma bond has newly formed, and then the double bonds have moved to these places. So this is the product which will again undergo tautomerization to that one. So if you get a question like this, don't be afraid. So it is as simple as we already have seen so many examples. So there are two oxygen functionalities and C3 and C4 carbon atoms. So this is the C3 carbon atom and this is the C4 carbon atom, right. So there are two oxygen functionalities over here. If you heat this molecule, definitely you can see the Cope rearrangement reaction, and in addition to that, after heating, if you put some sulfuric acid, you will be seeing this product. So you need to work out here. This is a simple thing only, no need to panic at all, and derive at that product. How we can do that? See, Cope rearrangement happens first, and then you will be getting a product. So what is the product after Cope rearrangement? I will be starting from here. So OH and OH and this, right. So this is the product. So this is moving like this and this is happening as well. So therefore you will be getting the product like this. So which is quite capable of performing tautomerization here. So what happens if it is able to show the tautomerization? So double bond O, double bond O. So we will be able to see this one, right. So in other words, you can also write this as double bond O, this one. Am I correct? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is the product which will be seen here. Because we are adding the acid here, so it can always have a chance of undergoing aldol condensation. Aldol condensation. Okay. So if it undergoes aldol condensation, so then you will get this product as the final product. So that's it. So no need to panic at all here. So this is how the questions will be. And once again I am telling you, like Cope rearrangement or Claisen rearrangement, which falls under the category 3,3 sigmatropic rearrangement reactions, are very, very, very important in the competitive exams. Okay. So please practice whatever the examples you see, and then we can solve if there is any difficulties in the next class. Okay. So in the next class, so we will see the Claisen rearrangement reaction. So which is also again the important part of the 3,3 sigmatropic rearrangement reactions. Okay. Thank you.